In this video, I would like to introduce you to parametric equations. Parametric equations are another way of graphing stuff. So this is one of my favorite pictures. I just think it's really cool looking. The way to do parametric equations, you define your x and your y coordinates separately. The equations for this graph, x equals t plus sine t and y equals t plus sine of 6t. Notice that both x and y have a periodic function in them, and if you look closely at this scribbly diagonal, you'll see that it repeats. I can see like a funky n and then a funky n. So we see that the scribbling is also periodic. Let's look at an example. Suppose I have x equals t squared minus 2t and y equals t plus 1. Now how might I figure out what that looks like? Well, I could do a t-chart, which I hate. I've always hated t-charts. But I can plot a few points and see what it looks like, sort of. I kind of get an idea of what it looks like, but it's not very satisfying. Another thing I could do is I see that y equals t plus 1, so I can solve for t and plug that back into x. And then I get this equation, which I can multiply out and factor and realize I've got a parabola on its side. This is a little bit more satisfying. I see that it's a parabola, but I've lost the information about the t. I've lost the timing of what's going on. The advantage of parametric equations is it not only gives you a path, but it also gives you timing on the path if t is equal to time. So if I put the two together, that's a little bit better. I like that. Another example. X equals cosine t, y equals sine t, where t is between 0 and 2 pi. One of the tricks we can use when we have cosine t and a sine t mixed together with our x's and y's is jiggle the terms using some of the things we know with sines and cosines and other trig functions. If I take x squared plus y squared, I get cosine squared plus sine squared equals 1, which is a circle. But there has to be more to it than that, because I've got all this t stuff. I could have just said x squared plus y squared equals 1 in the first place. Because I've defined x and y in terms of t, and t goes from 0 to 2 pi, I actually have a starting point and an ending point. So if I come up with a t-chart, I see that I'll start at 1, 0 and end at 1, 0, but I go all the way around the circle once. But what if I switch the x and the y? What if x is sine t and y is cosine t? It's still going from 0 to 2t. And I still have x squared plus y squared equals 1. So I still have the circle. The difference is where I start and where I end. At time 0, in this case, I'm starting at the point 0, 1. So I start at the top and end at the top, and I'm going counterclockwise. What else can I do? Let's say, well, there's lots of things we can do. Let's say I have x equals sine of 2t and cosine of 2t. What does that 2 do? Well, when you graph this stuff in trig, you know that 2t, by putting a 2 there, you've changed the period of the function. Instead of the period being 2 pi, it's now 2 pi divided by 2, or pi. So it's going twice as fast. Again, I'm going to have a circle, but since t is from 0 to 2 pi, and this period is half as long, I'm going to go around twice. So again, I'm going to start at 0, 1. The white spiral is just to show you the motion. I'm still in the yellow circle, but I'm going to start at 0, 1 and go around twice. Let's do one last example. Suppose I have x equals 2 cosine t and y equals 3 sine t. Now I can't just say x squared plus y squared because then I get something wonky in the front. But what I can do is solve each of these equations for their trig functions. So I have x over 2 equals cosine t, y over 3 equals sine t. Now I can square those and add them and get to my 1. Now what is that the equation for? That is an ellipse. When you have x squared over a squared plus y squared over b squared equals 1, that is an ellipse. Let's do our t-chart to see where we start. Well, at t equals 0, we have 2, 0, so we're going to start over on the right. The next one is 0, 3, which means we're going to go counterclockwise. So it looks something like this. That's the power of parametric equations. We're not going to get into the calculus of it just now, but I want to get comfortable with doing some of the graphing.